Now, we don't solve these, you're not expected to solve these graphically, although there is a graphical interpretation for every one of them. The method that we'll be using is either the substitution or the elimination method. So we're going to dive right in and just start solving several of these here. All righty. So this is a system of two equations and two unknowns, the first of which is a linear equation, but the second one is a nonlinear equation. The second one is going to be a circle. Now, for purposes of the final section in this chapter, we will need to touch base with the equation of a circle. So I'm going to show ourselves that equation right now. So this is an equation of a circle where the center of the circle is going to be the ordered pair HK. These coordinates are just the opposite of what sign you see here. So if you see the minus sign here, that means this is going to be a positive coordinate. If you see a plus sign here, this will be a negative coordinate. Likewise here. Okay, and the radius of the circle is just going to be equal to the square root of r squared, or just r. So this is the equation of a circle. All right. Now, to solve this system, we could use either the elimination or the substitution method, but the elimination method just is not really going to work here at all. So we really should lean towards the substitution method. So I'm going to have to take one of these equations and solve it for one of my variables. I'm going to take my first equation here and I'm going to solve for y. To do that, I add x to both sides. And then I'm going to divide or multiply both sides of my equation by -7. Oh, you know what? I should have solved for x instead here. Let's solve for x instead. It'll be a lot easier. We won't have fractions to worry about. Let's solve for x. So we'll solve for x by adding 7y to both sides. Now I'm going to multiply both sides of this equation now by a -1 to solve for x. And therefore, I have accomplished my task of solving for x. So another name for x now is -50 minus 7y. I'm going to take this expression and I'm going to bring it up here and substitute it in to my second equation in for x. So in for x goes -50 minus 7y, and that has to be squared plus y squared equals 100. So again, this -50 minus 7y I brought up and I substituted into the second equation for x. Now, having done that, the second equation collapses down to an equation involving only y, and then I'm going to solve for y now. So I'm going to have to FOIL this out. -50 minus 7y times itself. And of course, we're going to use our FOIL algorithm to multiply that out. Now, I'm not going to go through the elementary details because we've been FOILing out binomials for a long time now. So we're going to have -50 multiplied by itself will give you 2,500. -50 times -7y is going to be 350y plus another 350y be plus 700y. And -7y times -7y is plus 49y squared. So now we have this quadratic equation that we have to solve for y. There should be a plus sign here. So we got to solve for y now. Combining our like terms, I have 49y squared plus y squared. That's going to give me 50y squared. I'll put that out front. So just rearranging this so that this is in descending order. Subtracting 0 from both sides to zero this equation out. I will continue up here. $2,500 minus 100. I subtract 100 from both sides. Is going to be 2,400. And now I have to solve this quadratic equation for y. Factoring does not look very inviting. Let's see here. Well, let's see. Does 50 divide into 700 evenly? Yeah, it does 14 times. And 2,400 divided by 50 gives us 48 times. So, you know what we could do maybe is, what's that? I'm going to factor a 50 out. This will be 14y plus 48 equals 0. And can this trinomial be factored? Two factors of 48 that add up to 14 would be 6 and 8. So this trinomial factors into y plus 6 times y plus 8. Now we're going to set our factors equal to 0 and solve for y. So this one implies that we get y equals -6. Setting this factor equal to 0, solving for y, we get -8. But remember, solutions to systems have to be ordered pairs. So we got to find the x coordinates. Now to find the x coordinate, I'm going to use this equation here that's already solved for x. So when y is equal to -6, x is equal to -50 minus 7 times -6. X is equal to -50 plus 42, or is equal to -8. So one ordered pair solution would be -8, comma, -6. That's one ordered pair solution. The other ordered pair solution is found when y is equal to -8. When y is equal to -8, x is going to be equal to -50 minus 7 times -8. And this is going to be -50 plus 56, which is going to be 6. So another ordered pair solution would be 6, -8. So 6, -8. So there's two ordered pair solutions to this system of two equations and two unknowns. -8, -6, and 6, -8. Any questions how we solve this system? All right, so I use substitution there. Now, what would be the geometric interpretation? This would be the equation of a circle, and this circle is going to be centered where? Well, x squared is x minus 0 squared, and y squared is y minus 0 squared, and 100 is 10 squared. So this is going to be a circle centered at the origin with a radius of 10. A circle centered at the origin, 0, 0, and the radius would be the square root of 100 or 10. This is just going to be a line. That's just a linear function. Well, what I'm going to do is I'm going to graph those in Desmos and give ourselves a quick snapshot, ladies and gentlemen, as to what those two solutions look like and what they mean geometrically speaking. And now, the nice thing about Desmos graphing calculator is that your equations do not have to be solved for y like they do for your graphing calculator. You can just enter these equations in implicit form, just like this, and it'll still graph them. That's the beautiful thing about this utility. This is called Desmos Graphing Calculator, DES MOS, Desmos, graphing calculator. So we can see that the graph of the first equation is this red line. The graph of the second equation is a circle centered at the origin with a radius of 10. These two graphs do intersect at 2 points, and would you believe the 2 points of intersection are the two ordered pair solutions that we got by solving the system using the substitution method. And there you go. There's your two solutions. Any questions about this problem here? All right. So we solved it algebraically, but that's the graphical interpretation of what those two ordered pair solutions down here represent. Okay. All right, let's try another one. Here's a system of two nonlinear equations and two unknowns x and y. We want to solve the system. Notice since the second equation is already solved for y, I'm going to use the substitution method. So this 3 times the square root of x minus 8, I'm going to bring up, substitute it in for the y variable into the first equation. Upon doing that, my first equation becomes this. Now I'm going to solve this equation for x. I'm going to expand this out. X minus 5 times x minus 5 would give us x squared minus 10x plus 25. When you square this quantity, 3 squared is going to be 9. And when you square a square root, the square root disappears. So the square of x minus 8 is just x minus 8. Solving for x, distributing the 9 inside the parentheses. All right. It is a quadratic equation. I'm going to zero it out by subtracting 25 from both sides. And therefore, my quadratic equation in the variable x looks like this. Finally, combining my linear terms, I get x squared minus 1x minus 72 is equal to 0. Now, solving this quadratic equation, can we maybe solve it by using the factoring method? Are there two factors of negative 72 that add up to negative 1? The middle coefficient, and there are negative 8, 9. Negative 9 and positive 8, rather. So this factor is an x minus 9 times x plus 8. Set both factors equal to 0, solve for x. So one value for x is 9. Setting x plus 8 equal to 0, solving for x, we get x is also equal to negative 8. Well, we found our x coordinates of our ordered pair solutions. We have to find the associated y coordinates. And to do that, I'm going to use the equation that's already solved for y. So when x is equal to 9, we see that y is equal to 3 times the square root of 9 minus 8, which is 3 times the square root of 1, which is just 3. So one ordered pair solution is 9, 3. When x is equal to negative 8, put negative 8 in here. Y is going to be 3 times the square root of negative 8 minus 8. Y is equal to 3 times the square root of negative 16. Which means y is going to be equal. Now, the square root of negative 16 is really 4i. And 4i times 3 is 12i. And so they know when x is equal to negative 8, there will be no ordered pair solution to this system because our y coordinate is not real. It's imaginary. So you can toss this guy out. The only solution is 9, 3. So solutions can never have imaginary coordinates. They always got to be real coordinates. So again, when x is negative 8, y is not real. 12i. So that's why we don't consider x being equal to negative 8 or y equal to 12i. Your only solution is 9, 3. And we're done. Only one solution, 9, 3. Now, what would be the graphs of these? Just curious, the graphs. This is a circle, notice, and the circle would be centered where? Where is this circle going to be centered? And what's going to be its radius? Well, the center of this circle is going to be HK, so it's going to be 5, 0. And the radius is the square root of 25 or 5. So the graph of this equation is going to be a circle centered at 5, 0 with a radius of 5. This is just going to be the square root function, basically, that has been shifted 8 units to the right and also experiences a vertical stretching by a factor of 3. You remember what the parent function, y equals the square root of x, looks like? Its graph. That would look like that. So this graph has been shifted 8 units to the right. So this point's going to go 8 units to the right. And the y coordinates are going to be tripled. So this graph's going to go look like this. It's going to be shifted 8 units to the right. And also the y coordinates are tripled. All right, why don't we throw these equations into Desmos and convince ourselves that the only point of intersection between the radical function and the circle is 9, 3. So let's do that. You can see it is a circle centered at 5, 0 with a radius of 5. And you can see that our graph here, our radical function graph is in purple here. I'm going to show you what the graph of the basic parent radical function would be, y equals to the square root of x. And you can see, yes, that the basic parent function, square root of x, has been shifted 8 units to the right. And also its y coordinates have been tripled. It's experienced a vertical stretch. Everybody see that there? All right, what's that point of intersection? It would be 9, 3. And there is the only solution to this system, 9, 3. And we found that using the substitution method. Any questions about this problem? All right. Now, so far, we've used the substitution method. We've never used the addition method. When would the addition method be, warranted? Well, we would definitely consider the elimination method for a system like this. Now we're going to solve this system of 2 nonlinear equations and 2 unknowns. And by the way, these are not circles. These are called ellipses. Okay, ellipses are degenerate circles. And you're not expected to know how to graph the ellipse manually. So we're going to solve the system using the elimination method. So we have to make a decision. What variable do we wish to eliminate? I'm going to choose to eliminate y. Therefore, if this is 2y squared, I want this to become negative 2y squared. I can arrange for that to happen by multiplying my first equation by negative 2, of which I would then have the equivalent first equation as being negative 4x squared minus 2y squared equals negative 34. The second equation slides underneath this unaltered, keeping our like terms lined up. Now we add these equations together. Negative 4x squared plus 1x squared is negative 3x squared. The y terms are eliminated. And we're left with negative 12 on the right. Solving for x now, we divide both sides by negative 3. And x squared walks out of here with a value of 4. We now take the square root of both sides of this equation. Keeping in mind, please don't forget the positive or negative square root of 4 If you forget that, you're going to lose solutions. So don't forget the plus or minus. X is equal to positive or negative 2. So there you go. X is equal to positive, negative 2. Now we need to find the y coordinates when x is equal to positive or negative 2. All right, suppose that x is equal to positive 2. I'm going to use the second equation to solve for y. So replacing x with positive 2. And now solving for y. Subtracting 4 from both sides. I get 2y squared is equal to 18. Divide both sides by 2. Y squared is equal to 9. Take the square root of both sides of my equation. Don't forget the plus or minus square root of the number side. So y walks out of this with a value of plus or minus 3. And so, ladies and gentlemen, we're going to have two ordered pairs here. We could have positive 2 and positive 3, or we could have positive 2 and negative 3. But we're not done, because x could also be equal to negative 2. But ladies and gentlemen, I don't have to go through this same song and dance again, because look at, regardless of whether you put on a positive 2 or a negative 2 into this equation, because you're squaring x, it doesn't matter. You're going to get the same solutions for y. So if I was to put negative 2 in for x here, I'd get the same solutions for y. So therefore, if x is equal to negative 2, y would have to be equal to positive or negative 3. So here's your other two solutions, negative 2, positive 3, or negative 2, negative 3. We have 4 ordered pair solutions to this nonlinear system of 2 equations and 2 unknowns. There's all your solutions right here. Any questions how I got those 4 solutions to that system? By using the elimination method, I solved that system. Just so we can appreciate those solutions, the geometric interpretation can be shown by using, again, Desmos. So I will go there and throw these equations into Desmos and we'll graph them. So here we go. There's an ellipse where the longest axis called the major axis is vertical. And there's the graph of the second equation, which is an ellipse where the longest or major axis is horizontal. Notice these two ellipses intersect at 4 points. And those 4 points of intersection are precisely the 4 ordered pair solutions that we generated by solving that system using the elimination method. Any questions about this problem here? We'll look at another one here. This is going to be a parabola opening downwards, correct? Leading coefficients negative. And here's the second equation in our system. And this will be the graph of a parabola opening upwards because we have a positive leading coefficient. All right, so we want to see if these parabolas intersect at any points, because those points of intersection in the plane will be the solutions to this system of 2 nonlinear equations and 2 unknowns. I have a question. What method do you think would probably be maybe the way to go to perhaps solving this system? Elimination or substitution? What do you think? Anybody?
Elimination.
Well, if you use the elimination method, you know, it looks like it's good to go to get rid of the x squareds. I'll give you that. The x squareds will drop out, but we're still going to be left with x and what y, aren't we? That still looks like an issue there. You know what? Since both these equations are solved for y, I'm probably gonna, you know, just maybe use the substitution method. So I'm gonna literally set the right-hand sides of these equations literally equal to each other. And I can do that because they're both equal to y, the same thing called a y. So let's do that. Now, so what I'm really having to deal with now is solving a quadratic equation for x. And to do that, we usually like to zero these equations out and then go from there. So I'm going to drag everything over to the left side of my equation. I'm going to subtract x squared for both sides. I'm going to add 2x to both sides. And I'm going to add 3 to both sides. When I do that, the left side becomes negative 2x squared plus 8x minus 6, and the right side goes to 0. Fair enough? I'm going to factor out a negative 2 out of all 3 of these terms here. When I factor a negative 2 out, I leave behind a nice trinomial. 1x squared minus 4x plus 3. Ladies and gentlemen, can I factor this trinomial? Are there 2 factors of 3 that add up to negative 4? Do they exist? The answer is yes, negative 1 and negative 3. So this trinomial can factor immediately into the 2 binomials of x minus 1 and x minus 3. Now we can set these binomials equal to 0, the variable factors equal to 0. Don't set negative 2 equal to 0. And then we just solve for x. X equals 1 and x equals 3. Knowing x is 1 and 3, we have to find the corresponding y coordinates. So when x equals 1, I am free to choose any one of these equations up here to solve for y. It doesn't matter which one. I'll go with the second equation. So when x is 1, I'm going to put 1 in here, and crank out y. So y is going to be equal to 1 minus 2 minus 3, which is going to be equal to negative 4. Hence, one ordered pair solution would be 1, negative 4. There's one ordered pair solution. But we're not done because x could be equal to positive 3 also. So when x is equal to positive 3, I'll now put positive 3 in here, and crank out y. So we get 9 minus 6 minus 3, which is that 0? You know, I think it is. I do believe that is 0, isn't it? Yeah. All right, so another ordered pair solution would be 3, 0. So these would be the only 2 ordered pair solutions to that system. And we solved it by using the substitution method. Now, just for the sake of curiosity, I'm going to go back to Desmos and throw these equations into Desmos and just take a look at the graphs and convince myself that I do get these points of intersection here. There's the graph of the first one. And here comes the second one. And you can see that yeah, it does appear these graphs intersect at 2 points. And the 2 points of intersection would be 1, negative 4, and 3, 0. And ladies and gentlemen, we have solved this system correctly. Those are your points of intersection. Notice the purple graph is the parabola that opens upwards because we have positive 1 in front of x squared. The green graph is the parabolic graph that opens downwards because we have negative 1 in front of x squared for that equation. All right, so that one is now done. Okay. All right, ladies and gentlemen, I'm going to have you do classwork. Oh, wait a minute, hold on. There's one more I need to show you. One more I need to show you. Then I'll have you do classwork one. All right. I got to show you one like this next. You think it's possible for these nonlinear systems to have no solutions or infinite number of solutions? You think that's possible? Well, do you think it's possible to have two graphs in the XY plane, two different graphs that never intersect anywhere? I don't see why not. Let's try to solve this system, nonlinear system of two equations, two unknowns, and we will solve it by the elimination method, because that seems like the easiest way to go here. My decision is going to be, I am going to eliminate X. And I'm going to do that or accomplish that by multiplying my first equation by -1. Therefore, my equivalent first equation will be -x squared minus 4y squared equals -4. Sliding the second equation underneath this unaltered. Now adding these equations together, x is eliminated. The y's add up to -5, and the right-hand side goes to 5. Solving for y squared, we divide both sides by -5. And therefore, y squared walks out of this with a value of -1. Now we take the square root of both sides. Don't forget the plus or minus square to the number side. And we get y is equal to positive or negative what? What's the square root of -1?
1i.
I.
I, right? Yep, I. Well, look what happened here. I did everything legal. I subjected this system to the elimination method. I, tried to eliminate my x variable, and I was successful in doing that. But what happened is I end up with some non-real results for y. And because of that, ladies and gentlemen, we would slam on the brakes here and say that this system has no solution. So there is no solution here. No solution. Because we're not getting real results for y. These are non-real. So there is no solution to that system. I'm curious to find out what's going on with this system. By the way, just out of the sake of interest here, this would not be the equation of a circle. You see, to be an equation of a circle, the coefficients in front of x squared and y squared have to be the same. Here we have 4 in front of y squared, here we have 1 in front of x squared. This would be an ellipse, not a circle. It's called an ellipse. This would be neither a circle or an ellipse. It would be a hyperbola, called a hyperbola. Well, let's just throw these into Desmos and convince ourselves that there is no point of intersection between this ellipse and hyperbola. All right, here we go. Again, the reason why Desmos graphing calculator is so nice compared to our TI-84 is because for the 84, you'd have to solve these equations for y in terms of x, which would be a real messy affair, to say the least. With Desmos, you could just literally type them in implicit form, and it will literally graph the function or the relation. So you can see that the first equation does generate an elliptical graph. The second equation generates what's called a hyperbola. And these graphs do not intersect anywhere. For that reason, there's no solution to this system of two nonlinear equations and two unknowns. And that's why when we tried to solve it using an algebraic technique, the elimination method, we ended up with this situation here. because that indicates there's no solution to the system. Okay. All right, now we're ready for classwork number 1. Unless there's any questions about this here. All right. Okay, so classwork number 1, I'll have you try a couple. Number 1, I want you to solve this system here. You know, just so we're on the same page, ladies and gentlemen, let's solve this system. What method do you think might be the way to go here? Elimination or substitution? What do you think? Does this thing look like it's designed for the elimination method? Doesn't look too good because we got x squared and y squared. We don't have any of that in this equation here. All right, let's use the substitution method. So we're all on the same page. Here's what I want you to do. I want you to solve this equation for x and then go from there. Okay, that's the first one. And I want you to solve this system here. Now, this second system is designed for the elimination method. That's the way you want to go. All right, ladies, I want to give you a little bit of time to work on that, see if you can crank out the ordered pair solution or solutions to those systems. Oh, I do apologize. For the first system, it should be x minus y is equal to 2. So I do apologize that there, ladies and gentlemen. So it should be x minus y is equal to 2. There you go. But still solve for x in terms of y. All right. All right, let's take a look at number one. Now I solved the second equation for x by adding y to both sides. So x is equal to 2 plus y. And then I substituted that in to the first equation and for 2 plus y and for x everywhere. And then I solved this equation for y. Again, all my like terms. Then I factored a 4 out of each of these three terms, factored the trinomial down. By the way, this happens to be a perfect square trinomial. Set y minus 1 equal to 0, solve for y, you got 1. And then I used x equals 2 plus y to solve for x. When y is 1, you got 3. The only solution I'm getting is 3, 1. Did anybody get that there? 3, 1.
Yeah.
Yeah.
That's the only ordered pair solution I'm getting. 3, 1. All right. Okay. So that's the end of that problem there. So that was the substitution method. Now the second problem really is designed for the elimination method because we got our x squareds, y squareds, and constants lined up. So I went by that route. And I decided to eliminate the y variable. I multiplied my first equation by 2. Then adding the equations together, y is eliminated. And I'm left with this equation in x, this quadratic equation of which I use the square root method to solve it. And I get x is equal to plus or, I get x is equal to plus or minus 2. Now, as I'm going to solve for the y coordinates when x is plus or minus 2, we don't have to split this up because if you use like your second equation or your first equation, doesn't matter, and you put positive or negative 2 in for x, because you're squaring the value, you're going to get the same solution for y anyways. So I just put positive and negative 2 in for x, the whole shebang there. And I squared it and walks out with a value of 4. Then I solve for this quadratic equation for y. And I get y is equal to positive or negative 3 when all is said and done. So here's our 4 solutions. X could be positive 2, y could be positive 3 or negative 3, or x could be negative 2, in which case y could be positive 3 or negative 3. There's your 4 solutions. Did anybody generate those?
Yes.
Okay. And those would be your 4 ordered pair solutions to that system there. Everybody understand how I could just put positive and negative 2 into like the second equation for x? Doesn't matter. You can do both at once because you're squaring the results. That's why. This walks out with a positive 4 either way. Whether it's positive 2 in here or negative 2. That's why you can take care of all of that all at once. Okay. All right. There we go. So in this section, we discovered how to solve nonlinear systems of equations by either using the substitution or the elimination method. And we've seen that in some of these cases, you could get maybe more than one ordered pair solution. And there is always the possibility that there would be no solution to such a system, which is certainly possible. Just remember, any ordered pair solutions to these systems always have to have real coordinates. You can never have an imaginary coordinate for x or y in an ordered pair solution. Okay, just remember that. They got to be real coordinates. All right, well, to wrap this lecture up today, we have just one more section and we'll close out chapter 5. 5.5 will have us solving inequalities in 2 variables. Now we've solved inequalities in 1 variable before, But how do we solve them in two variables? Well, actually, these inequalities in two variables are going to have an infinite number of solutions. And because of that, we cannot enumerate all the solutions. And so we're going to have to graph the solution set. And so graphing paper really should be used when you do this. And I am going to go grab my graphing paper. Okay. We'll start off by just solving one of these, and then we'll eventually learn how to solve systems of these. All right, so here is a linear inequality in two variables, x and y. We wish to solve it for its ordered pair solution set. A solution to this must be an ordered pair, and the ordered pair has to satisfy this inequality to be a solution. I'm just curious, can anybody think of any ordered pair that would satisfy this inequality or that would make it a true statement? Can anybody think of any ordered pair solution? Anyone? You know, I could think of one. How about 1, 0? The ordered pair 1, 0, would that be a solution? If you put 1 in for x and 0 in for y, isn't 3 times 1, 3? Isn't 3 less than 6? So 1, 0 would be an ordered pair solution. Are there any other solutions?
0, 0.
0, 0 would be a solution. That works. 0 minus 0 is 0. 0 is less than 6. That's true. All right. Would 10, 0 be a solution? 3 times 10 is 30. 30 minus 0 is 30. 30 is not less than 6. This would not be a solution. Doesn't work. In fact, there are an infinite number of solutions. So, I mean, we can't just sit here and enumerate all of them. We'll be here till the end of time. So how do we represent the solution set? Well, we have to graph it. Okay. So step number 1 is we have to graph the associated boundary first. So we must graph the associated equation. Got to graph the equation first. And how do we do that? Well, there's many ways to graph a linear equation. You could get this in the slope-intercept form if you want to. Or you could use maybe some other technique. I'm going to use the XY intercept method. So how do we find an x-intercept? We always set y equal to 0. Put 0 in for y. The equation collapses down into this. We can now solve for x. And we get x equals 2. Correct? So my x-intercept is 2, 0. What's my y-intercept? How do we always find a y-intercept? We always set the other variable x equal to 0. Take 0, substitute it in for x. And now we can solve for y. This is gone, so we're left with this. Divide both sides by -2, and y walks out with a value of -3. That's your y-intercept. Now that we know our x and y-intercept, we can easily plot these points in the xy plane and put a line through them. But, ladies and gentlemen, there's something else we need to understand. We need to look at our inequality. And if we either have a strictly less than or a strictly greater than inequality symbol, then we are always to use what's called a dashed boundary. Which indicates that any point sitting on the boundary will not be a solution to the inequality. If, on the other hand, we have the equal sign as part of our inequality, either less than or equal to or greater than or equal to, then we would always use a solid boundary. whereby any point that lies on the boundary would be a solution to the inequality. Notice I have a strict inequality, so I'm going to use a dashed boundary. In other words, when I plot these points, I'm going to put a dashed line through them, not a solid line, but a dashed line. So let's go get our piece of graphing paper and plot those points. So 2, 0, I'm assuming my tick marks are spaced by 1 unit apart on both axes. And then 0, -3. There we go. Put a line through these points, but it has to be a dashed line. And we have graphed the boundary in the XY plane. That's the boundary. Everybody understand how we graph this linear equation first as the boundary by finding its X and Y intercepts. All right, the only other part of this problem that remains is we now need to determine whether we shade the plane above and to the left of this dashed line or below and to the right to determine the infinite set of ordered pair solutions to this inequality. There's two ways, ladies and gentlemen, of determining on which side of this line to shade. Two ways. Method number one is by choosing a test point that clearly lies on one side of the line. And you know what? The nicest test point you could possibly work with is the origin, 0, 0. The only time you cannot use 0, 0 is if the boundary actually goes through 0, 0. But because my dashed line does not contain 0, 0, I can use 0, 0 as my test point. So I'm going to ask myself, is 0, 0 a solution to the inequality 3x minus 2y less than 6? Is it true or false? Well, we replace x with 0 and y with 0. And we ask ourselves, is this true or false? Is 0 less than 6 true or false? That's true. So the answer is yes. 0, 0 is a solution to the inequality. Because of this, we shade the plane that contains 0, 0. If 0, 0 was not a solution to this inequality, then we would have to shade the plane on the opposite side of the line that does not contain 0, 0. But because 0, 0 is a solution, we shade this away. And you are looking now at the graph of the solution set to that inequality, that linear inequality in X and Y. Any point that lies in this shaded region would be a solution to that inequality. Any point that lies in the unshaded region would not be an ordered pair solution to the inequality. Any point that lies on the dashed line is not a solution to the inequality. Okay, and that's your answer. That's one way to determine on what side of the line to shade. The other way, ladies and gentlemen, is to do this, to remember this. If you were to take this inequality and solve it for y, such that y is on the left side of your inequality, and if this is true, if y is either less than or y is less than or equal to something, then in that case, if you have this, we would shade below the boundary. But if y is greater than or y is greater than or equal to, again, y is being on the left side of the inequality. In this case, we would shade above. We would shade above the boundary. Okay, so that's another way to determine on what side of a line boundary to shade. If you just solve your inequality for y always being on the left side of the inequality, you can determine what side of the line to shade, what plane, what side of the line to shade, depending upon whether you have less than or equal to, or greater than or equal to. Let's convince ourselves. Notice I shaded above this line boundary here. But it looks like we have less than. What's going on here? Well, would we have less than? If you were to solve this inequality for y by subtracting 3x from both sides, and then dividing both sides by a negative, what happens when you divide or multiply an inequality, both sides of the inequality by a negative? What do we do with the inequality symbol? Do you remember?
Flip it.
We would have to flip it. And for that reason, you can see that, yes, y would be greater than. And because y is greater than, we shaded above the line. Everybody see that there? Okay, that's why. That's why we shaded above the line. So whether you want to use test points, pick a test point on one side of the line to determine what side you shade, or if you want to solve your inequality for y, make sure y is on the left though. You can also then determine on what side of the line to shade based on what your inequality looks like in relation to y. Okay? Leave that up to you. Any questions how we solved or graphed the solution set to this linear inequality in x and y? First, we graphed the boundary, the associated equation. And then we decided or determined on what side of the line we have to shade to denote the solution set. You can either choose a test point on one side, in which case I did by choosing 0, 0, finding out it was a solution, hence I shade up here. Or you could solve your inequality for y, in which case you would discover y is greater than something, which means you shade above the line. All right. Notice we have a dashed boundary because we have a strict inequality, not the equal sign. Any questions about that first one? Okay. Try another one here. 4y is less than or equal to 3x. We want to solve this inequality for its infinite ordered pair solution set. To do that, first we have to graph the associated boundary. So we got to graph the associated equation first. So we really got to graph this linear equation. This is very close to being in slope-intercept form. In fact, if I was to divide both sides by 4, I would have this equation literally in slope-intercept form. So what is my y-intercept? Y-intercept is 0. My slope is 3/4. Because of that, I think we're good to go to graph this thing immediately. So plotting the y-intercept, which is the origin, 0, 0, and knowing the slope is rise over run, 3/4, I can, starting at my intercept, y-intercept, go up 3, 1, 2, 3, and 4 to the right. 1, 2, 3, 4, plot another point. I can do that again, up 3, 1, 2, 3, 4 to the right. 1, 2, 3, 4, plot another point. Would I put a solid or a dashed line through these points here? Solid or dashed line?
Solid.
Solid line, because we have the equal sign as part of our inequality. So I'm going to put a solid line going through these points, these collinear points here, and we have graphed the boundary. The only thing that remains now is determining on what side of the line to shade to denote or round out the rest of the solution set of ordered pairs for this inequality. You can do that one of two ways. You could choose a test point that clearly lies on one side of your line, or you could, solve your inequality for y. By the way, if you solve for y, the inequality, you would see that you have this here. So based on the fact that y is on the left side of the inequality, and we have less than or equal to, where am I going to shade? I will shade not above the line, but below the line. So we're going to shade below. Or suppose you don't want to do it that way. Suppose you want to choose a test point. Well, be my guest. And it doesn't matter what side of the line you choose your test point. I'm going to choose a test point above the line. How about the point 0.5? I'm going to test out 0.5 in my inequality and see if it's a solution. So I'm going to test the point 0.5. And notice 0.5 clearly lies above my boundary. That's my test point that I decided to choose. You could have chose one down in this plane also, It doesn't matter. You got to choose one on one side. Why can I not use 0, 0? Because the boundary goes through 0, 0. You got to choose some other test point. All right. So I'm going to test out 0, 5 in my inequality here and see if it's a solution. That means I replace y with 5 and x with 0. So is 4 times 5, is that less than or equal to 3 times 0? Is that true? Is 20 less than or equal to 0? Is that true? This is false. And because this is false, this indicates that 0, 5 is not a solution to the inequality. Because of that, because 0, 5 is not a solution, ladies and gentlemen, we have no business shading the plane that contains 0, 0 because it's not a solution. We got to shade on the other side of the line. That's why we shade down below. Okay. Now, had I chosen a test point in this plane down here, I would have discovered that it is a solution, which would then also indicate that I shade below. So do we understand how to shade? Whether you choose a test point, test it out to determine on what side of the boundary you shade, or whether you solve your inequality for y and then look at how the inequality is oriented with respect to y on the left to determine how you shade. It's up to you. Okay. So that one's done. Any questions about this one here? The solution set of this one here. So can anybody give me a solution to this inequality? Give me a solution to this inequality. Read off a solution. Anything. There's many to read off. Just give me one.
1, -1.
1, -1. Does it lie in the shaded region? Yes, it does. It must be a solution. How about this point up here that lies on the line? Would it be a solution? That point that lies on the line right there.
Yes.
Yes, it would. This is a solid line. And any point that actually lies on this line would also be a solution to the inequality. Would this point way down here of whose x and y coordinates, I don't have a clue, and I wouldn't even be able to read off from the graph. Nonetheless, is it a solution, this point? Yes, it is. It's in the shaded region. This plane goes forever, okay? That's a solution. There's an infinite number of ordered pair solutions in this plane because this plane, the shaded plane extends in both directions forever and goes down and to the right forever also. Infinite number of solutions. All right. Now this one looks weird. This next one here. If I told you to solve this, your first thought would be, if this is out of context and it's not in the section 5.5 here, your first thought would be, well, wait a minute, we've already done ones like this before. This looks like it only has one variable. And if we were to graph the solution set, we would graph it on the number line. Do you agree? By putting a bracket shading to the left. We've done that before, did we not? But ladies and gentlemen, if this is deemed as being a linear inequality in two variables, x and y, then this is not good enough to denote the solution set. It must be a shaded plane that consists of all ordered pair solutions to this. So I would have to specify that this is indeed an inequality in two variables, x and y. You're probably wondering, well, where's the y variable? Well, it's there. It's just that it's preceded by a coefficient of 0. Because it doesn't matter what y is, x must always be less than or equal to -1. That is a fact. So I have a question here. How do we graph the solution set for this inequality in two variables, x and y? First, we have to graph the associated equation. Can anybody tell me what the graph of x equals -1 would look like? What is the graph of this? What kind of a line would this be?
Vertical.
The vertical line. And it has to go through the x-axis at -1. And would it be a solid or a dashed vertical line?
Solid.
Got to be a solid vertical line going through the x-axis at -1. So let's take a piece of graphic paper and show that. So here we go. There's the boundary. Now, the next question is, do I shade the plane up to the left of this vertical solid line or to the right to represent the other infinite ordered pair solutions to this inequality? Well, think about it, ladies and gentlemen, it's pretty simple. To encounter ordered pairs that have x coordinates that are -1 or less than -1, I would have to go where? To the left of the line or to the right? What do you think? What do you think? Left or right? If my x coordinates of my ordered pair solutions are to be less than or equal to -1, where do I shade?
Left.
You got to go to the left. You go to the right, the x coordinates are going to be bigger than -1, greater than -1. No, x coordinates must be less than or equal to. So this is pretty obvious. You got to shade to the left here. And you got it. Done. There's your solution set to x less than or equal to -1. That was an easy one to solve. Pretty simple, huh? Because the graph is just a vertical line. All right. So any point that lies to the left or lies on a vertical, a solid line would be a solution to this inequality, technically in two variables, x and y. All right, that one's done. All right. So far, all of our inequalities have been linear inequalities. Is that always going to be the case? The answer is no. We could have nonlinear inequalities, so we better start addressing a couple of these. So let's try this one here. Solve x minus 2 squared plus y squared greater than 9. So we want to solve this nonlinear inequality in x and y for all of its ordered pair solutions. How are we going to do that? Well, first of all, we're going to have to graph the associated boundary. So we got to graph the associated equation. And can anybody tell me what kind of a graph this is going to generate? It's not going to be a line. That's not a linear relationship between x and y. It's not a parabola because that's not a quadratic relationship because both x and y are squared. Anybody tell me what kind of graph that's going to be? It's going to be the graph of a circle. That's it. Now, and where would be the center of this circle? Can anybody help me here? What's the center of this circle? Well, it's literally HK.
Is it like 2, 0?
0. That's the center. And what's the radius of this circle? It's the square root of 9, which is 3. There you go. All right. Now, again, be careful of these coordinates here. I always tell people, like, the sign of the coordinates are always opposite the sign. So if you see a minus sign here, this coordinate must be positive. What if we had a positive? What if I had x plus 2 squared plus y, let's say minus 3 squared is equal to like 64. Suppose I had this circle here. What would be the center of this circle here?
-2, +3?
Yeah, it's got to be a -2 for the x coordinate. It's all because the sign of the coordinate is always opposite the sign you see.
So do you solve for y as well? So would it be negative or +3 or is it
positive 3? That's +3. Just remember, the sign of the coordinate is always opposite the sign you see. So if you see a plus sign, the coordinate must be negative. You see a minus sign, the coordinate must be positive. Always opposite. And the radius for this circle would be the square root of 64 or what? Or 8. Okay. All right. Do we understand how to determine the center coordinates of a circle and whether they would be positive or negative coordinates now? All right. But this is not the circle we're dealing with. Let's get back to our problem. Our problem is right here. We need to graph this circle whose center is at 2, 0 and has a radius of 3. And would it be a solid boundary or a dashed boundary? Solid or dashed? It's got to be a dashed circle, if you will, or a dashed boundary. So take a piece of graphing paper And we will try to graph that circle here. So my circle centered at 2, 0 right there, and the radius is 3. That means if I go 3 to the right of the center, 1, 2, 3, I'd plot a point on my circle. If I go 3 to the left of my center, 1, 2, 3, I plot a point on my circle. If I go up 3 units from my center of my circle, 1, 2, 3, I plot a point on my circle. If I go down 3 units from my center, 1, 2, 3, I plot a point on my circle. Now I need to connect these points with a nice circle. And I don't have a, let's see here. Well, you know what? I do have something called a what? Anybody know what the name of this thing is? You ever see one of these before? That's called a compass, and enables you to trace circles very nicely. What you do is you put one of your points at the center of the circle, and then you put the other point at a point on the circle, and then you basically just spin this baby around, spin it around, and it makes a nice circle. You can buy one of these at the dollar store. But this thing is not the best. It's kind of cheap, ladies and gentlemen. You get what you pay for, and there's a good example. But anyway, I'm just going to freehand this one. Wish me luck. I'll just do the best I can do here. All right. All right, that's not too bad for freehanding it. So there's our circle, but I made a mistake because it should be what kind of a boundary? Should not be solid, it should be dashed. But we're in luck because I also bought this at the dollar store. Whiteout, my best friend. So I will make it a dash boundary. No problem. Now we have a dashed boundary. Do I see that there? A little bit of whiteout. The only other thing that remains is we need to determine whether we shade inside the circle or outside the circle to represent all the other infinite ordered pair solutions to this inequality. Now, unfortunately, shading above or below the boundary is kind of like out of business now because this is not just a line graph, it's a circular graph. We really should choose a test point in this situation, Lizone. So can anybody give me a nice test point that I could subject to this inequality to see if it's a solution? I'm staring at a real nice test point. Does anybody know which one I'm staring at? How about the blank of the circle? What's that called? How about use the center of the circle as a test point? It's available. So we're going to do that. We're going to test out 2, 0 in my inequality. That means X gets replaced with 2 and Y gets replaced with 0. X is 2, Y is 0. So is 2 minus 2 squared plus 0 squared greater than 9? This is going to be 0. Is 0 squared plus 0 squared greater than 9? Is 0 greater than 9? Is that true or false? Is 0 greater than 9? That is false. So 2, 0 is not a what? Not a solution to the inequality. Because of that, ladies and gentlemen, we don't shade the plane that contains 0, 0. We don't shade inside the circle because 2, 0 is not a solution. We must shade outside of the circle. You are now looking at the graph of the solution set to that inequality, that nonlinear inequality. Any point that lies outside this circle here is a solution to this inequality. Any point that lies on the circular boundary would not be a solution to this inequality. Everybody understand how I solve that
Yes.
circular inequality for its solution set there? Okay. Now, you know, this is a beautiful thing about Desmos. You know, being an online course here, ladies and gentlemen, you really have kind of a luxury going on for yourselves here because you got access to Desmos, okay? Whereas in class, my people don't have access to Desmos, especially when doing an exam. So you have a little bit of a luxury going on out there. So here's what you can do. You can type in this inequality in Desmos here to kind of check your answer. Now, greater than, there's a greater than symbol on your keyboard. So you literally just type it in and that's what you get. Everybody see that there? You are looking at the solution set. The solution set is literally any point that lies outside of this circle. And there's an infinite number of them, obviously, correct? If you keep zooming out, you can see this shaded plane just keeps getting bigger and bigger and bigger and bigger and bigger. All right, pretty cool. All right, so you got Desmos to complement things in here. What a luxury that is, huh? All right, so that one is done. Now it's 1:53 and the clock is starting to win the war. So we better start now looking at how to solve systems of inequalities in X and Y. More than one of them, called systems. And let's see if we could just dive right in and try one out here. There's one. Here comes another one. This is called a system of two linear inequalities and two unknowns. And we wish to graph its solution set. To do that, we're going to have to graph not one, but two solution sets. And the idea is this: where the shaded regions overlap will be the solution set to the entire system. All right, so we have to do one of these at a time. First of all, let's graph the first boundary of the first inequality, which means we have to graph this first equation. Hey, but we're lucky here. This thing's already in what form? That's in slope-intercept form. So immediately we know the y-intercept is 2 and the slope is 1/2. That's more than enough to graph this. Will it be a solid or dashed line? This is going to be a solid line. Solid line. Take a piece of graphing paper. And let's graph y equals 1/2 x plus 2. The y-intercept is 2. And the slope is 1/2. So for every 1 unit I go up, I go 2 to the right. Up 1, 2 to the right, plot point. Up 1, 2 to the right, plot point. Up 1, 2 to the right, plot point. I put a solid line through them. Solid line. Solid line through these points. And I have graphed the boundary of the first inequality in that system. Do I shade below or above this line? What do you think, ladies and gentlemen? I don't even think we need a test point here. It's a line. We have y on the left. We have less than or equal to. That means we shade where? Above or below? That would be below this line. I'm not actually going to shade this whole plane below the line because it gets messy. You know what I'm going to do? I'm going to put a couple of arrows kind of pointing down to the right and below this line. That indicates that I've shaded below this line. Just a couple arrows there. This comes in handy when you start solving many inequalities in the same plane. Instead of cluttering your graph up with so many shaded regions where it's so hard to see what's going on, I just kind of like put little arrows in relation to the boundary. Okay. All right, now we got to do the next one. This one here has to be solved. To do that, first we have to graph the associated boundary, which is the equation 3x minus y equals 3. Easiest way to, in all honesty, ladies and gentlemen, graph this linear inequality is just to find the x and y intercepts. The x-intercept is found when y is 0. If this is 0, then 3x equals 3, which means x is equal to 1. That's your x-intercept. To find the y-intercept is equally easy. Just let x be 0 now. Put 0 in here. This term drops, and we're left with -1y equals 3, which means y is -3. There's your y-intercept. Plot the points. Connect them with what kind of a line? Solid or dashed? This will be a dashed line. So we got 1, 0. and we have 0, -3. And I put a dashed line through these points. Make sure you always put arrows at the end of your lines. Very important there, okay? Now I just have to determine whether I shade above and to the left or below and to the right of this dashed line. You can do this one of two ways. You can choose a test point clearly on one side of the line and see if it satisfies the inequality, or you could solve this inequality for y and then look and see what direction your inequality points, with y being on the left to make the determination. If you were to solve for y here, you would subtract 3x from both sides. But then you'd have to multiply or divide both sides by a -1, which means you'd have to flip your what? Inequality symbol around. So ladies and gentlemen, you be the judge. Would I shade above the dashed line or below if y is greater than? Greater than. Since y is greater than, we shade what? Above and to the left. You can again just put like little arrows here. This indicates you would be shading above and to the left. Okay, we're almost done. Now, where do these regions overlap? The shaded regions overlap. Well, in relation to this boundary, I'd be shading below and to the right. In relation to the dashed boundary, I'm shading above and to the left. Where the two shaded regions overlap is going to be right in here. You are looking at your answer. This is the graph of the solution set to this system of two linear inequalities and two unknowns, x and y. Any point that lies in this triangular, this increasingly larger and larger triangular plane, if you will, it's getting larger and larger as you go down, because these lines are diverging. They're getting what? Further and further apart from each other. Or any point that lies on this boundary here, up to this point of intersection here, would be a solution to the system. Notice any point that lies on this boundary would not be a solution because this is a dashed line, dashed line. This one's solid, okay? And there's your solution set. We're done with that system. So can anybody read off for me a nice, convenient, ordered pair that would be a solution to this entire system? That would be a solution to both inequalities simultaneously. Give me a solution, nice one.
0, 0.
0, 0 lies in the shaded region. Therefore, it must be a solution to the entire system, which means it must be a solution to this inequality and this inequality simultaneously. Let's just check it out real quickly. This is 0. This is 0. Is 0 less than or equal to 2? It checks out. Put 0 in here and 0 in here. Is 0 less than 3? It checks out. Do you agree? 0, 0 works. You are correct. 0, 0 would be a solution to the entire system. All right. Do we understand how we solve that system of two linear inequalities and two variables x and y by shading the overlap of the two solution sets? And it's the overlap of the solution sets of the individual inequalities that constitutes the solution set of the entire system. Okay, entire system. That one is done. Okay, clock 2:01. All right, so ladies and gentlemen, let's try maybe one more. And I think I'm gonna let you guys play around with maybe with a class work here. Okay. So I need this one here. I want to kind of keep this graph here. So. All right, so here's the system here. It says y is less than or equal to negative x squared plus 7. Y is less than or equal to negative x plus 5.
Is this the classwork or are we just?
No,
doing
this I'm going to do this one here.
Okay.
And I'll maybe give you one last one. So we're going to try to solve this system of inequalities by graphing the solution set. So we have three inequalities to deal with here. First of all, this one, what would be the graph of y equals negative x squared plus 7? This is a quadratic function. It would be a parabolic graph. Does a parabola open upwards or downwards? It would open downwards. By the way, this quadratic function happens to be in what's called vertex point form. Do you remember good old vertex form? Y is equal to a times x minus h quantity squared plus k. That's called vertex form, where the vertex point is the ordered pair hk, which in this case is going to be 0, 7. That's the vertex point. And that's the vertex point, 0, 7, 0, 7, hk. And the parabola opens downwards because a is -1. And it's less than 0. Parabola opens downwards. That means the vertex point would be a maximum point. Okay, let's see if we can look at this. By the way, for a more accurate plot, since the vertex point is above the x-axis, 1, 2, 3, 4, 5, 6, 7, and the parabola opens downwards, it's going to have 2 x-intercepts because it will cross the x-axis at 2 points down here. To find the x-intercepts is pretty easy. You just let y be 0. So that means you're going to let y be 0 here, and you're now having to solve this quadratic equation, which is easy to solve. Just use the square root method. You could just add x squared to both sides of the equation and then take the what? Square root of both sides. You got your 2 x-intercepts, positive or negative square root of 7. Now, for plotting purposes, what is the square root of negative square root of 7? Approximately. Now it's about 2.6. So these are approximately plus or minus 2.6. Those are your x-intercepts. Just plot those approximately. Negative 2.6 is about here, and positive 2.6 is about here. Will this be a solid or a dashed boundary for this parabola? It's going to be a solid boundary, and this parabola is opening downwards. Should be a nice smooth turning point here, not a sharp kink, by the way. Okay, well, I'm a little off there. All right, now we need to make a determination. Will we shade inside the branches or outside of the parabola to give us ordered pair solutions to this quadratic inequality? To answer that question, ladies and gentlemen, you could use a test point, but this kind of works the same way, in a way, as a line would work, okay? Because my y is on the left side, and I have less than or equal to, that means to encounter ordered pair solutions to this quadratic inequality, I would have to shade below these parabolic branches here, not above them, but below. So I'm going to be shading this away. I'm just going to put some arrows to indicate that I would be shading inside these branches. Suppose you didn't want to do it that way. Suppose you want to choose a test point. Well, suppose we chose 0, 0 as our test point. And if I put 0 in here and 0 in here, is 0 less than or equal to 7? Is 0, 0 a solution to this thing? Looks like it is, right? 0 is less than or equal to 7. That's why, again, we are shading inside the branches of the parabola, okay? So whether you want to choose a test point to determine that, or just look at this, y is less than or equal to, you shade below the boundary. That's okay in this case. All right, that one's done. How about this one? Y less than or equal to negative x plus 5. First, we have to graph the associated equation. We got to graph y is equal to negative x plus 5. Well, it's easy to graph this because the y-intercept is 5 and the slope is -1. So I can plot 0, 5 and then go down 1 and 1 to the right to plot other points, since the slope is -1. So up 5, 1, 2, 3, 4, 5. There's the y-intercept of my line. Now to plot other points, I go down 1, 1 to the right. 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 Will be a solid or dashed line. It's going to be a solid line. Solid. So we put a solid line through these points. Now, would I shade below or above this solid line? Look at, notice y is less than or equal to. That means we shade below. Do you agree? So we're going to shade below. Put some arrows indicating that this is the direction you would shade in relation to this solid line boundary. Shade this away. Okay, one more, y is greater than 1. We have to solve this inequality. What is the associated equation? Y equals 1. What kind of a line is this to say y equals 1? Vertical or horizontal?
Horizontal.
It's a horizontal line, and it would be a what? A dashed horizontal line. Notice that goes through the y-axis at 1. Take your ruler, put a dashed horizontal line through the y-axis at 1. Here it is. Now, do we shade above this dashed horizontal line or below? Well, look at, we got y on the left and we got greater than. That means we shade above the dashed horizontal line. We shade above. Based on how all my arrows are pointing here in relation to these boundaries, where would be the overlap between the shaded regions? Can you see? Do you agree it would be what? Right in here? This is the overlap between all shaded regions. Now, if you guys want to use colored pencils or crayons or markers, go ahead and do that. I like to use little arrows because I just have one color, namely this pen. And so that way I don't clutter up the whole darn thing. It's easier to see what's going on. There you go. That would be the graph, the solution set of this entire system of 3 inequalities and 2 unknowns. As long as the point lies in this shaded region or on this boundary from here to here, here to here, or here to here, but not on this boundary. This is dashed here. It would be an ordered pair solution to all 3 of these inequalities simultaneously. Can anybody give me a solution to this entire system? Can you read off an ordered pair in that shaded region? Any nice ordered pair?
Zero, 2.
0, 2. Let's see. 0. Yeah, 0, 2 is in the shaded region. It would therefore be a solution to this inequality, and this inequality. 0, 2 would be a solution to the entire system. Exactly right. You are correct. Now, what if I picked a point? Look at this. Check this out. What if I picked a point down here? Can anybody tell me, this is a rather challenging question, but can anybody tell me this point down here? Can anybody tell me, all right, first of all, is this point a solution to the entire system? This point down here?
No.
No. But of which inequalities is it a solution of? That's the challenging question. Of which inequalities in this system is this point a solution of?
The first 2.
Yeah, it'd be a solution of the first one because it's inside the parabolic branches. It's a solution of the second one because it's below and to the left of this solid slanted line. But it's not a solution to the third one because it's not above this dashed horizontal line. Exactly. That's why this fails to be a solution to the entire system, because it's not a solution to the third inequality. It's only a solution to the first 2. Okay? That's why it has to be a point in here that satisfies all of them. Right? Okay, classwork, and then we'll wrap it up. I have a problem for you. I want you to try this this problem here. I want you to solve graphically this one right here. Let me think here. I'm thinking for a second. Hold on. Okay, here it is. X. Okay, it's just going to be x squared plus y plus 1 squared equal to 25. Wait a minute. Hold on. I'm still thinking. Less than or equal to 25. That one there. And here comes the other one now. Y is greater than the absolute value of x. Ladies and gentlemen, I want you to solve that nonlinear system of 2 Oh, wait a minute. Oh, I'm not done yet. Hold on. There's one more. And also this one. X is greater than or equal to 1. I want you to solve this system of 3 inequalities in 2 unknowns by graphing the solution set. This will be your last classwork. Or we could call this a classwork 1 for the road. How does that sound? Okay, go ahead and see if you can do that problem. Graph the solution set to that entire system. All right, so the first inequality, the boundary is going to be a solid circle centered at 0, -1 with a radius of 5. And I tested out the center point 0, -1 in the inequality, and it is a solution. 0, -1 is a solution to this inequality. So we would shade inside the circle. As far as y greater than the absolute value of x, we're going to shade above y equals the absolute value of x. And of course, the absolute value of x, y equals absolute value of x, is a V-shaped graph opening upwards, where the vertex is at the origin. And then x greater than or equal to 1, we shade to the right of x equals 1, which is a vertical solid line going to the x-axis at 1. And when you basically do all that shading, you'll see that the regions overlap right in that little region there. That's where all three shaded regions overlap, because we had to shade above the absolute value. We had to shade inside the circle. We had to shade to the right of the vertical solid line. That would be the overlap. This would be what it looks like in Desmos. You type them all in, you can see that the overlap between all shaded three regions is right in here, kind of like this little piece of a pie right here. They're right in here. So any solution that lies on this circular boundary from this point to this point, from this point, from that point to this point, any point that lies on this circular bound, I'm sorry, on a circular boundary, I'm not from this point. That's the wrong, that's no good. It's got to be from this point to this point, would be a solution. Notice a point that lies on this absolute value portion of the graph is not a solution. That's a dashed line. But any point that lies on this vertical line, x equals 1, would be a solution from this point to this point of intersection down here. Okay. You would find these points of intersections between all of these boundaries by solving systems of equations. That's how you'd find these points of intersection here. Obviously, Desmos can find them a little bit quicker than we can. Just by clicking on them, you got them basically. So did anybody get that for the solution set for this entire system? This little wedge piece here? This,
Yes.
and that would be it right there. Any point in here would be a solution to all three inequalities. All right. So I will post on Canvas a preview for the Chapter 5 test, along with the solution. So you might want to just look at that. I'll open up the rest of the Chapter 5 Alex homework and the Chapter 5 Alex quiz, which will be due by midnight, April 4th. Midnight, April 4th, which is next Tuesday night. Okay. And of course, I'll make available the exam next Tuesday on Chapter 5. All right. Well, have a good day. If you have any questions, I'll hang on the line for a couple of minutes here.
I just private messaged you at the beginning of class. Did you it said that the other assignments that were due like last Thursday, we could turn on Friday, it would just be the 10-point deduction. And I had worked like doubles almost like the last 2 weeks. I've worked like 40 hours. So I was trying to do it. I only had time to do it on Friday, and I went to go do them, and it wouldn't let me do them. Did you close them so we could do them on Friday?
That was on Friday. You went to do them?
Yeah, it said they were all zeros, and so I checked and made sure, and it still said that we could still submit it on Friday. Again, it would just be like the deduction.
The 24th, correct? Okay. All right. Well, what's your last name? Green?
Yeah.
All right. I'll go investigate that. And if
Yeah, because I went to go do the additional problems for it. It was the only thing that was like even like showing. Everything else was just put as zeros. And
now,
it said
what problem? What sections were these? Do you remember?
I don't remember. Just they were all put as zeros. I was gonna do them on Friday, and they said they were due the Thursday night, and then but it said you could submit them on Friday for the 10% deduction, you know. And so I went to go do them, and then they were all closed and all put as zeros.
All right. Were they in chapter 5 or chapter 3 and 4? Do you remember?
I think it's 3 and 4.
3 and 4? Okay.
Yeah.
All right, I'll look at those and I'll get back with you, okay, as to
Okay.
what I'm gonna do with those, okay?
Okay, thank you. Because
Alright.
I had emailed you Friday morning. I know you get like a lot of emails, but I had emailed you to try to open them up so I could try to do them on Friday. And said,
All
I
right,
didn't get a
I'll take a
response.
look at them,
Weekend.
Callie. All right.
Okay, thank you.
I'll get back with you. Yep.
Thank you so much. Bye.